Welcome to this lecture on front-end and back-end in Fintech, where we'll frame the relationship between user-facing interfaces and the server-side systems that power financial flows. Think of the front-end as the interactive dashboard and wallet users touch, and the back-end as the resilient, compliance-first engine that enforces rules, stores, records, and settles money behind the scenes. On the back-end side, we focus on a few core responsibilities: enforcing business rules, storing immutable transaction records, integrating with banking APIs, and applying risk models in real time. Typical technology choices include Java Spring, Node.js, and Python Django, while infrastructure patterns rely on PCI DSS, compliant networks, and horizontal scaling, and data integrity is preserved through ACID guarantees for every money movement. Secure API communication is a two-way story. The front end exposes stable REST or GRPC contracts, signed requests, and versioned endpoints so clients can evolve safely, while the back end enforces mutual TLS, short-lived JWTs, rate limits, and exhaustive logging, ensuring each call is authenticated, auditable, and compliant with RegTech reporting requirements without leaking sensitive references. A decoupled, event-driven architecture uses message brokers like Kafka or RabbitMQ to turn user actions into events, allowing the front end to emit non-blocking payments or state changes while separate backend consumers, an idempotent ledger service, notification engine, and analytics pipeline process those events asynchronously, ensuring eventual consistency, real-time UI updates, and resilient scaling under load. Fintech security practices span both sides. Front-end defenses use CSP, SRI, and aggressive input validation to prevent injection and XSS, secure token storage with encrypted HTTP-only cookies and rotated refresh tokens, while back-end systems maintain comprehensive identity, event, audit trails, and a coordinated security posture so that prevention, detection, and logging work together across the stack. A layered back-end security framework starts with a web application firewall and API gateway to filter and monitor HTTP traffic, moves to a service mesh implementing mutual TLS and zero-trust role-based access controls, applies transparent data encryption for files and transaction logs, and preserves immutability via append-only ledger tables with cryptographic checksums validated during compliance audits. Front-end optimization strategies aim for fast, efficient experiences. Keep first input delay under 100 milliseconds and compressed bundle sizes near a 150 kilobyte target. Use code splitting to load modules on demand, employ service workers for caching and prefetching next pages, and optimize origin hits to reduce cloud egress costs while maintaining snappy interactivity and predictable load behavior. Back-end scalability and data consistency depend on microservices scaling, sharding, caching, and replication. Use Kubernetes horizontal pod autoscaling for stateless services, shard Postgres by account UUID, front hot state with Redis clusters and atomic scripts, and rely on write-ahead logs plus global read-only regions to support multi-asset trading while preserving high availability and data integrity across geographies. The end-to-end architecture flow shows a Flutter wallet front-end using biometric authentication, cached exchange rates, and clear pending states, talking to a GraphQL orchestration layer that coordinates Plaid for account linking, Stripe for payouts, internal FX services, and a double-entry ledger. The system guarantees idempotency and consistent orchestration, so user intents become correct, auditable settlements. Key system optimizations combine performance, security, and cost efficiency. Migrating to gRPC and HTTP, two can cut end-to-end latency by roughly 35%. Deploying a TensorFlow microservice for real-time fraud detection can push fraud below 0.02%, and tiering cold data to Glacier plus spot instance batch jobs can yield around 18% cloud cost savings while keeping operations reliable. AI-powered fintech optimization brings front-end and back-end together via copilots that generate plain language requirements and backend policy code to shorten release cycles, federated learning that preserves PII locally while sharing model insights to improve fraud scores, and smart contracts that auto-reconcile payment intents with backend settlement records to enable faster, low-error automated settlement. A secure event-driven integration pattern combines a lightweight front-end, a secured event-driven integration layer, and a strongly governed backend, so that zero-trust identity, idempotent APIs, horizontal scalability, and measurable performance budgets translate into trustworthy financial experiences that regulators, partners, and users can rely on for consistent, auditable, and scalable operations.